Today we are going to speak about the second half of the topic of this series of lecture, which is formal geometry. And if before I gave some sloppy proofs, now the proofs became even less frequent. I will state many statements without proof because it requires a long background in commutative algebra and so on. So let's start with what is the idea behind the formal geometry. And this will be very informal. I take a disk. So this is this. And I can look to the of the ring of holomorphic function in on the disk, and I have a map from this to C of double of the ring of power C's, which send a function in its Taylor expansion. And actually it happens that this map is injective. And this means that, and as everybody knows when it studies this complex analysis, that this means that I can read many properties of the functions just by looking to their power series expansion. And it happens that this is not an isomorphism, but this is a much algebraic object than this in some way. So the idea is to try to push this consideration in general algebraic geometry, and essentially try to say, okay, I cannot look to analytic to holomorphic function, but I can look to their I can look algebraically to their Taylor expansion. And the idea is to work only with Taylor expansion. So in order to do this, I would like to remark that C of double parenthesis T as an ideal, which is T, and this ideal to the power n has the nice property that C double parenthesis T over T to the power n is isomorphic to C T to the power n. And why I like this isomorphism? Because this object is a sort of bridge with holomorphic function, and this object is purely algebraic. So this will be used to build this bridge between analysis and algebraic geometry. So the idea now is take A to be a ring, and A be an ideal, And I can look to the ideal, to the ring A to the power A divided by A to the power n. And actually, this has a natural morphism to A divided by A to the power n minus 1. So I can build a ring, another ring, which is the limit to A divided by A to the power n hat. And just to understand what I did here, I have this ring, and I consider this, and if I look to C of T hat, this is thus C double by this construction. And I will say that A is small a adically complete if A is isomorphic to A hat. Actually, not just by an arbitrary isomorphism, because I forgot to say that I have a natural map from A to A hat. And before I forget, from now on, all the rings will be Noetherian. All the rings here. Some difficult stuff arrive in non-Noetherian rings. And actually, just to say, this hypothesis nowadays is quite restrictive. Why I say nowadays? Because recently there have been a lot of mathematics around formal and A-adic geometry by Scholz and so on, and they use things which are not Noetherian. So this makes life much more difficult. But I will not enter in this kind of difficulties. And I can do the same if M is a module. I can introduce M hat is just the limit of M divided I M, and the things are a little bit easier if M is of finite type. I have then M hat is just M tensor A hat. And so you see, in order to prove all of this, you see a lot of commutative algebra to deal about. And okay. Let me see. Before I start, yes, okay. Now I can introduce the formal spectrum. So given A, I can introduce and an ideal A. I can introduce the formal spectrum of A, let's say around A divided by A. And this is defined in the following way. How it is defined? So this is denoted by formal spectrum, formelle of A. I suppose that A is complete. Suppose this. Actually, you don't need it. So this is a ringed space. And so the topological space is just a spectrum of A divided by A. Be careful, just the topological space, not the ring of it. Then for every n, I can consider the ring A divided by A to the power n. The sheaf associated to this is a sheaf on this space. So OX, which is by definition the limb of A divided by A and sheaf, is a sheaf on this space, and I will define the formal spectrum of A to be the couple spec A divided by A, and this ring, this sheaf of rings over this. No, I will not. No, actually, I am not using this. I just say that but you use it in the here.
Sorry, what do you mean by this ring?
When you have okay, you have I can look to the so I have the spec of A. Okay, inside spec of A, this is a closed set which is spec of A divided by A. Okay, now over here I have a ring, I have a sheaf, call this space, this scheme X. I have a sheaf which is this. Inside here I have an ideal sheaf which is I will denote it by I don't know, EA. Okay? Now I can look to the sheaf OX divided by EA to the power n. This sheaf here, since we are in over the spectrum of an affine scheme, is associated to the module over this ring. And the module, actually, this is just A divided by A to the power n, and the sheaf associated to this. Okay? And actually, the support of this is exactly this closed set. Okay? So this is actually a ring. Okay? So I can consider this as a sheaf over this. Okay? It's not. You don't look. It's not a sheaf of. It's not a sheaf of A over A module. It's just a sheaf. Okay? And now I can look to the limit of OX divided by EA to the power n is another sheaf, which I will call OX, like this. And now this is a sheaf over this topological space. And it's a sheaf of rings over this topological space. And I will call, by definition, this topological space with this sheaf of ring. This becomes a ringed space. And this ringed space is the formal spectrum of A hat. Okay? On big A? In order to construct this, I had to use big A. Yeah? I had to use big A, otherwise. But remark, so example. Take A to be C of T, and as ideal T. And the formal spectrum of is a point. So remark the formal spectrum is of the completion. Yeah, but this is because I was thinking I can erase that because I can take any ring and then I will construct this. This is the correct thing. Okay? Sorry, can you? Exactly. Exactly. A hat, yeah, but I will see this in this example. So this is a point as a topological space, but as a ring, as a ring of regular function is C of T. Because A hat is the limit over C of T divided by T to the power n, which is C of T. Okay? So you see that this formal spectrum topologically is just a point, but the ring of regular function is much bigger. Okay? And I will give you another example. You take A to be C2, and with coordinate x and y, and then you take as an ideal y. So it is a line. This corresponds to a line inside C2. Okay? Now I can look what is the formal spectrum of A hat. This will be spec of C of y, C of x, sorry, because I kill y. Because, yeah. And as a ring of regular function will be C of x, but with double with formal series along y. Okay. Yeah. But this is just, yeah. This is a ring. Then you should associate what I'm saying. This is the global. So will be the global section of the thing. It's just to, okay. So if you want, you can do this. Okay. So how you can imagine this? This will be a line, but a function. If you imagine. This is not totally true because not every power series converge to a holomorphic function, but just imagine that, and then just imagine that every power series corresponds to a holomorphic function. So it's a line plus a holomorphic function defined. An element here will be morally a line plus a more holomorphic function defined over as a germ of neighborhood of the line inside the plane. You see, this what is it? This is an holomorph. What is an element here? It will be an holomorphic function such that if you restrict this holomorphic function to the line is a polynomial, but is not a polynomial. Something like x e to the power y. This is an element which have a very nice description inside here. Okay? So anyway, so this is the intuition behind the formal spectrum. And another example, just to show that we are earning something, you take A to be spec of Z, small a to be a prime ideal, and then if you take, you can consider the formal spectrum of A completed. It will be spec of Fp with as a ring of sheaves Zp, the completion of Z at P, the ring of p-adic integers. Okay? So in this, with this uniform construction, you will build up this object and this object, which are much more algebraic, much more from number theory, let's say. And once you build up So how you construct schemes? Schemes are we are a ringed space which are locally spectrum of a ring. And now you build it, so let's say that schemes are geometric objects which are built up by small bricks, which are affine schemes. And once you understand what should be bricks, you can build other theories. So now we build the bricks of a new theory, and we will say what is a scheme, what is a formal scheme. A formal scheme X is a ringed space which is locally isomorphic to SPF of A hat for some and you have an important thing is that okay, you can define sheaves, coherent sheaves, and so on formal schemes, just as you do on any scheme. You can define sheaves will be a sheaves which is coherent if it is okay. You can do on any ringed space. You can define coherent sheaves and so on. And you also have what is a morphism between formal schemes will be morphisms between ringed spaces. And you have just to show something about morphism. Yes. Yes. So in particular, I will say that X is a couple X0 and OX. You see it as a ringed space. So it's a topological space and a sheaf of rings. And you can even define dimension of the formal scheme. And in order to do this, you will do it as the maximal length of ideal subsheaves, of chains of ideal subsheaf of your structural sheaves, like you do for schemes. But you have to be careful, because let's look to this example. The topological space is 0-dimensional, it's 1 point. But inside this, you have the ideal T, which gives you a non-trivial subscheme of your scheme, of your total scheme. So this scheme, this formal scheme, even if it has dimension 0 underlined topological space, it is a formal scheme of dimension 1, because, and if you use your intuition, what this should be a neighborhood, a small neighborhood of a point inside a line. So a small neighborhood keep the dimension of the, it must be an open set, let's morally speaking, so it must be of dimension 1. Same thing, you can play your exercise and see that this is of dimension 2. Okay? In some way, I'm trying to convince you that, okay, there is a big machinery of commutative algebra to develop formal geometry, but if you are a geometer, you can when you can alone at home, you can think about formal schemes as neighborhoods or neighborhoods of subvarieties inside varieties, and the intuition almost always work. Okay. And in particular, I want to say that there is a theorem, proposition, let X be a formal scheme then there exists an ideal sheaf EX with the property that the support of OX divided by EX is the total space X0. It's the underlying total space. And be careful, I didn't make a mistake. I say there exists a, not a unique. There is and this sheaf is called ideal of definition of X. And here is him. He is an ideal of definition, but be careful, also this is an ideal of definition. There can be many ideals of definition of your, this is not canonical. And here you will have as an ideal of definition this, but you can also have y. This is an ideal of definition of your thing. You can also have even this. What do you mean? Sorry?
What if you take the ideal to be 0?
You are right. Yeah, I forgot to say something. Yeah, you are right. I will say, you will say more like this is such that no. Okay, let me see what I would say that. Yes, this is the point, is that the support is of O divided by E x0 is x0, and, sorry, I forgot to say this, the couple x0 O E x0, sorry, x is now is a Noetherian scheme. This is I forgot to say. Yes, sorry. I had in back of my mind, but
does this imply that the sheets of sections is a direct limit of the
yeah, this is what I wanted to say in a second. Yeah.
It implies that?
Yes. But it's a theorem. It's absolutely not evident. It's not trivial at all. It is called Artin-Ries theorem. It requires, yeah. So, yeah, sorry, you were right. So you see, you can construct an underlying scheme of your formal scheme, and you will prove that exactly OX will be the limit of O x divided by which is called Artin-Ries lemma. You see, you once you start with this, and then from this, anyway, is a sort of it is a sort of way of saying exactly what you remarked. It's a sort of say that the formal scheme is complete. Okay, because you remember that a ring was complete where it coincided with its limit. And here we are saying that the sheaf coincided with its limit. And so this will be called the ideal of definition of your scheme, of your formal scheme. And something which generalized the construction of gosh, I am very late. Something which generalized the construction of the construction of the formal spectrum is if the main example is let X be a scheme and Y in X be a closed subscheme, then I can build up. I can construct a formal scheme, which is usually denoted each hat y, which is as a vector, as underlined space is Y, and as a ring of sheaf of structural sheaf is the limit of OX divided by the ideal sheaf of Y to the power n. Okay? This is exactly what we did here and what we did in the example before for in the example before for so if we take 0 inside A1, we will find the example I had before, the bind and C. And if I take a line inside A2, I will find the line and C of. So this construction is a generalization of what we did before, but for general scheme. And we have two things which are very important to remark. The first thing is if you take x and y equal to x, which is a closed set inside x, you find that the completion of x in x is just x. X with is structure sheaf, which is structure. So that means that this remark, which seems a little bit useless, but it says that schemes is a subcategory of formal schemes. So, for instance, there is no pain to speak about a morphism between scheme formal schemes to a scheme, which is very nice because when I write that there is this morphism, I can imagine it from the point of view of intuition as in X I have a closed set, and this is just a neighborhood, a formal, it's called usually it's called a formal neighborhood, but this can be also seen as a tubular neighborhood of Y inside X, and this has a perfect meaning in this language. So all the theorem you can, all the question you can ask about formal or about tubular neighborhood of in analytic geometry, you can now ask them. Yeah.
So in that case, the dimension of the formal scheme is the equal dimension of Y.
No, it's the dimension of X.
In that case, the dimension of that.
In this case, yes. Because there will be, let's say, things like this. There will be all the chains of closed set in Y, and then you can, there's this standard theorem that any change that you can have this chain of Y, and then you can go further, extend to a chains on till the dimension of X. Okay? So the dimension of this is exactly the dimension of X.
When you take a normal cube in a main.
Exactly, exactly. Yeah. Once you start to feel comfortable with this sentence you just say, many things are natural, but you can check and they work. And so this is the first. This no. This yes and no. I mean, no. I mean, topologically, yes. I mean, topologically, the image is a closed set. But the point is that you cannot say that if you have a closed set here, the image will be closed. It is, I mean, you have to be careful what is the definition of closed set. Because if you say that a closed set is just closed in the topological sense, is okay. But if you take a closed set to be an ideal in your stuff, it is not said. Okay? It's more delicate. And once again, if you have a...
So you mean for the second case, a closed scheme, subscheme?
Exactly.
Formal subscheme does not come from X.
You break all the surprise. I mean, exactly. This is the main question, one of the main questions in this topic. No, I'm just kidding. No, I wanted exactly. Following the suggestion of Philip, I want to make an example. And you take X to be the completion of A1 in 0, and Y to be the completion of A2 in 0, 0. And then you have a map. So let's do this. From X, okay, I call Z to Z, and this map will be given by which sends X in T and Y in sum of t to the power n over n factorial. This is exactly what. This will gives you a formal subscheme of Z. You see, because it's given by surjection. A formal subscheme of Z, Z as a map to A2, but as a formal subscheme, it is not coming from a closed set inside here. This is morally the curve t e to the power t, which is not algebraic. So you cannot obtain this curve algebraically, okay? But it can be described analytically in the formal setting. So and this is even a general theorem that in characteristic 0, formally you can always solve differential equation. This is a solution of a differential equation, but you cannot do algebraically. Not every. And now we go further in the Grothendieck point of view, which is you should think about functors and okay, no. Since we are speaking about this example, I will say that definition, a formal scheme is algebraizable a formal scheme X if x is isomorphic to x, y for some scheme x with a subscheme y, closed subscheme y. Okay? And it happens that next week both will speak about one of the main very interesting topic in this subject is how to be able to recognize when a formal scheme is algebraizable or not. I don't know if I have time, but I will try at least to describe rapidly tomorrow an example of formal scheme which is not algebraizable. So, which is really, which looks naturally, but it is not algebraizable. And as you see here, at least this example should be in your head to see that it is possible even to have a formal morphism between algebraizable schemes which are not algebraizable. So this is easy to describe. Okay? Huh? Yes, you can, but the graph will be non-algebraizable. Yeah, that is okay. That is okay, but there are also other examples which looks more. So the point is this: the graph is not algebraizable as a sub. So is a closed formal subscheme which is not algebraizable as a subscheme, but itself it is algebraizable. So, but there exist formal schemes which are okay.
The graph is abstractly algebraizable.
The graph is this. The graph will be isomorphic to this. But you cannot. Abstractly is algebraizable, but there are formal schemes which are absolutely not algebraizable in the abstract sense. This is the main difference. Okay. And the problem of algebra, so since it is I hope you feel the proximity with analytic geometry here. So the problem of things which are algebraizable is often related with the problem of existence of some line bundles with property, like an algebraic variety, a complex variety is projective, as we said in Chow lemma, if it has an ample line bundle. And now, and here the situation is similar, so we have to study a little bit vector bundle or at least coherent sheaf on formal schemes, which is, gosh. So what I want to say, which is very useful, is that if I have, this is a general theorem, that this morphism is flat. And this is due to the fact that this morphism is flat. The proof that this is flat is commutative algebra, can be found in Matsumura, in Liu book, in many books. And this implies directly this, because flatness is property. So that means that you have a map from coherent sheaf of X, a functor, to coherent sheaf of X hat, Y, and this is exact, is an exact functor. and one on gosh. I would like to remark the following thing, that if you have a formal scheme, X formal scheme, you have, by definition, these schemes these are usual schemes which are closed in X. So, and usually these are denoted by Xn. You can imagine that this is the schemes, the underlying space with a sort of small neighborhood around it. So you have a sort of and you can see this as a filtration of your formal scheme. It's like, just to remember the example, you will have the point and C of t, and then you have a spec of C of t divided by t to the power n, which is inside here. So if you want, if you prefer, you can put your closed your double parenthesis, and you see that this is sort of looking to holomorphic function and kept their Taylor expansion at the order n minus 1 actually. And you have this filtration of your formal scheme. And actually, this happens also here. So you have this filtration, and if you have x and y inside, you can look to the scheme the v of OX divided EI to the power n, which I will call it y as yn. And actually I have a filtration y0 contained in y1, contained, no, y1, contained in y2, contained in yn, contained in x. They are all schemes contained in x, but actually it happens that this has a formal scheme, and they are also subschemes of it, or even better. You have so you see that inside X you have a sort of filtration of closed subscheme where each are supported on Y, but you are taking a small neighborhood, small small, let's say, neighborhood of y inside X, and this neighborhood are also neighborhood of y inside the formal completion, which essentially you imagine this as the limit of all the possible neighborhood in X. And so this is a way to really see the formal completion as a tubular neighborhood of X. Okay, gosh, I am very late, but tomorrow I will speak about, I will at least state two of the main theorems you need to work in this context. Thank you.